Have you ever stood in, a big urban parking lot, maybe during a rainstorm,
Yeah.
and you see all that water sheeting across the concrete, and then whoosh, it just vanishes down a storm drain?
Yeah, it's such a common sight, isn't it? We almost don't even register it anymore.
Exactly. It's like our cities are built to just push water away,
Yeah.
get rid of it. But have you ever actually stopped and wondered, like, where does all that water go?
It's a really important question because that water isn't just, disappearing.
Right.
It's usually funneled into these huge, expensive underground pipe systems. And eventually, it dumps everything, all the pollutants it picked up off the pavement, straight into our rivers, our lakes, maybe even the ocean.
Mhm.
And doing that, it completely messes with the local water cycle. Plus, it means our groundwater tables miss out on getting refilled. We're basically sending away this precious resource and spending a fortune doing it.
And that is precisely the problem we want to unpack today.
Mm.
What if, what if there was another way? A way to manage that stormwater runoff that wasn't about just getting rid of it, but maybe inviting it back, cleaning it in the process.
Mm.
Well, that's where today's deep dive is heading. We're going into honestly, the really ingenious world of bioretention cells.
Yeah, these are fascinating.
They're not just pretty planters you see sometimes. They're these innovative, nature-based solutions,
Mm.
a really key part of what's called low-impact development, or LID. You'll probably hear us say LID a bit. And our mission today really is to give you a shortcut to understanding them. We want to peel back the layers, look at what they actually are, how they work, which is pretty cool, the different kinds you might see, and why they're such a powerful tool for, well, a more sustainable future.
It's all about figuring out how we can work with nature, recharge those water tables, clean things up, and maybe, just maybe, rely less on all that massive, expensive concrete infrastructure we were just talking about.
It really does sound like a game changer. And you mentioned it's not just the environmental wins like filtering out pollutants, but there are economic benefits too.
Oh, definitely. Both sides of the coin.
Okay, well, let's get started then. Let's unpack how these things actually, function.
Great. So at their very core, bioretention cells are these LID features, and they're specifically engineered to get rainwater moving downwards right on site, immediately.
So where it falls, basically.
Exactly. Think of them like localized sponges and filters, kind of woven right into the city landscape.
Sponges and filters. I like that. So it's about catching the water right away at the source before it picks up speed and pollutants.
Precisely.
Okay, but what are these sponges actually made of, and where do you usually see them pop up?
Well, the design seems simple, but it's very effective. It's basically a mix of specific plants and carefully chosen porous materials.
Porous materials, okay.
And you'll typically find them placed very strategically right next to those impervious surfaces we mentioned.
Like parking lots?
Parking lots, yeah, or maybe those strips of land you see between a road and the sidewalk, those kinds of places.
Ah,
These are the spots where runoff is a really immediate problem.
okay.
So putting the cells there means they can capture that water that would otherwise just, wash straight down the drain.
So definitely more than just a bit of decorative landscaping then. These are engineered systems, living systems,
Yeah.
and you said they have a kind of triple threat function, collecting, filtering, recharging. What part of that really stands out to you?
That's a good question. I mean, all three are absolutely crucial. But if I had to pick one thing that always impresses me, it's the efficiency of the filtration.
Really? How so?
It's not just passive. These systems are designed to pull out like up to 90% of suspended solids.
90%. Wow.
Yeah. And that includes everything from regular sediment to microplastic stuff that traditional storm drains just let right through.
Microplastics too, that's huge.
Yes. And they can also really cut down on nutrient loads, things like nitrogen and phosphorus, which stops them from polluting our waterways. So that active on-site cleaning before the water even leaves the immediate area, that's pretty revolutionary.
That microplastic stat alone is quite something.
Yeah.
Okay, let's get into the mechanics though, because that sounds like where the real cleverness is.
Yeah.
How does a bioretention cell actually take water pouring off, say, a parking lot and transform it like that?
Okay, it's a really neat step-by-step process. First, water from those hard surfaces, it gets directed into the cell. Often it's just a little dip in the curb or an opening, not a big grate.
Subtle.
Yeah, then once the water's inside, that's where the magic happens. The porous materials kick in.
The stuff you mentioned earlier.
Right. Engineered soil mixes usually a specific blend of sand, compost, topsoil, designed for good drainage, but also to support microbes that help break down pollutants. And there's often rock media too. All this allows the water to soak in really quickly. Infiltrate is the technical term.
So the ground just drinks it up.
Exactly.
Yeah.
And as that water moves downwards, and even sideways a bit, the plants get involved.
Yeah, plants.
Their root systems, plus all the microbial activity in that special soil, they actively filter out and absorb pollutants. They're literally cleaning the water as it passes. And then finally, after all that natural purification, the cleaned water slowly, steadily makes its way down and recharges the local groundwater table, back where it belongs.
That sounds incredibly elegant,
Yeah.
especially when you compare it to the old way, the sort of brute force approach of traditional stormwater pipes.
It really is.
Let's paint that picture. Think about a standard old-school parking lot versus one designed with these bioretention cells. The difference must be pretty stark visually, too.
Oh, completely. A traditional lot, you've got those continuous curbs all the way around, right?
Yeah.
Everything's angled to funnel every single drop towards the drains.
Into the storm sewer.
Exactly.
Right.
Which leads to this huge, mostly invisible network of underground pipes, culverts, maybe detention basins. And the entire point of all that civil engineering is just to get the water away. Send it somewhere else, usually a river or the ocean.
So a massive amount of engineering, construction, money, just to move the water. It does feel a bit like, I don't know, like our cities were designed by very determined beavers, always damming and redirecting everything.
That's a good way to put it.
And then you've got the constant expensive upkeep for all that hidden plumbing. And the key thing is the water is just gone from that spot. It never gets back into the ground right there.
Precisely. Now, contrast that with these newer bioretention designs. Instead of solid curbs, you see deliberate dips or opening.
Right, I've seen those.
They let the water flow straight into the bioretention cells. And you often find these cells tucked in behind sidewalks, maybe in the median strips, or even running between the rows of parking spaces themselves.
Okay. And what's actually in those cells that makes them work? Because I admit, sometimes I've seen them and just thought they were planters, maybe looking a bit messy after a big rain.
They can look a bit messy, that's true, but that's often them doing their job.
Yeah.
They're much more than just decorative. Typically, inside, you'll have a layer of rock media, often in the center. That helps handle larger volumes of water quickly, lets it infiltrate fast.
Okay, the rocks.
And then, usually on both sides, you have those carefully selected plants doing the filtering work on debris and dissolved pollutants. Some designs are really clever. They use raised concrete parking blocks, the wheel stops.
Yeah.
They elevate them slightly so water can actually flow underneath them and into the cell. Maximizes the capture area.
Smart.
And yeah, after a storm, they might collect leaves and stuff. But that's a sign they're working, catching the gunk the storm drain used to just swallow.
It really does sound like a whole different way of thinking. This active drinking of the water instead of just shedding it off. Does it come with any trade-offs? Like maintenance or maybe initial cost?
Yeah.
Things people should know?
That's a really important point. Yes, bioretention cells do need maintenance. It's more like landscaping work, really weeding, removing excess debris sometimes, making sure the plants are healthy.
So different from cleaning out giant pipes.
Very different. And in terms of initial cost, sometimes it can be comparable to traditional systems, maybe even a bit higher if you only look at the upfront construction cost.
Okay.
But, and this is a big but, when you factor in the long-term picture, less need for those massive pipe networks, reduced pollution downstream, boosted groundwater levels, maybe even fewer flooding problems. The overall economic case often swings heavily in favor of bioretention over the life of the project.
Right, the whole life cycle cost.
Exactly. It's about working with the water cycle, which usually turns out to be more sustainable and, yeah, ultimately cheaper.
It's fascinating how elegantly they work.
Yeah.
But, thinking about how different urban areas are busy downtowns versus quiet suburbs, it makes me wonder, are all bioretention cells the same? Or are there different types for different situations?
You've hit on a really key point there. No, it's definitely not a one-size-fits-all situation. The specific goals you have for managing water and filtering pollutants at a particular site will really determine which type of cell is the best fit. There are basically 4 distinct types.
4 types. Okay, let's dive into those. What's the first one? Infiltration recharge. What's that all about?
Right, so this type is your go-to when the main goal is just getting as much water back into the ground as possible, maximizing that groundwater recharge.
Okay.
You typically use it where the soil underneath is already naturally pretty good at soaking up water, permeable. It lets the water move straight down without spreading out too much sideways.
That makes sense.
The really critical thing here, though, is that the existing soil has to be able to handle the volume of water you're sending its way. If it can't, the system just backs up, overflows. So, yeah, perfect for places with good natural drainage that really want to boost their local aquifers.
So you need cooperative soil for that one to really shine.
Got it.
What's the next approach then?
The second type is filtration partial recharge. Now, this system is designed for spots where you need a really high level of pollutant filtering, but maybe getting all the water back into the ground isn't feasible or perhaps not the top priority.
Okay, so filtering is key here.
Exactly. Some water still gets recharged, which is great, but any extra water or water beyond a certain flow rate gets directed away through an underdrain system. This just helps the cell manage different water loads without getting totally swamped.
And I guess the plants you choose for this type are even more critical, right, for targeting specific pollutants. Can you give us an idea of how effective they are? Are certain plants good at grabbing certain nasty things?
Oh, absolutely. Plant selection is hugely important here. For example, if you've got high nutrient loadings, like nitrates from fertilizers washing off lawns or fields,
Right, a common problem.
then plants with really extensive root systems working together with specific soil microbes can be incredibly good at breaking down and absorbing those nitrates. Certain wetland plants, for instance, are basically nature's purifiers. They perform phytoremediation.
Phytoremediation, cool terms?
Yeah, they essentially clean the water using their own biological processes. So you choose those specific plants for these filtration-focused cells.
Okay, so we have maximum recharge, then high filtering with partial recharge. What's number 3? You mentioned a dual action system.
Right, the third type, infiltration filtration recharge. This one really tries to do both jobs well. It aims for significant filtration and significant groundwater recharge. It's particularly useful, again, where you might have those high nutrient loads, like nitrates, similar to the partial recharge type.
What makes it different in design?
These often have a bit more reservoir space built in, like a deeper layer of gravel or engineered soil. This gives the water more time to hang out, infiltrate, and get cleaned.
More contact time.
Exactly. And they often feature something called a raised drain.
A raised drain. How does that work?
It's pretty clever. It's basically an overflow pipe, but the opening is set a bit higher up within the cell.
Ah, okay.
So water has to rise to that level before any excess starts draining away. This maximizes the amount of water that gets infiltrated and filtered first. It's like a safety valve for really heavy rain, preventing the whole system from getting overwhelmed, but still prioritizing those main jobs, filtering and recharging.
That makes a lot of sense, especially for places with really intense sudden downpours.
Yeah.
Okay, finally, the fourth type, filtration only. The name sounds pretty serious, like it's for sites where contamination is a major worry.
You've got it exactly right. This system is tailor-made for locations where there's a high risk of significant runoff contamination, and you absolutely positively cannot let any of those pollutants seep into the groundwater.
Like where? What kind of places need that?
Think about gas stations, with potential fuel spills, or large transportation hubs, bus depots, train yards. Also, transload facilities, where they're moving freight between different modes, like train to truck or maybe ship to truck.
Okay, lots of potential for spills or leaks there.
Definitely. These are areas where chemical spills, oils, heavy metals, other industrial pollutants are a real, constant risk.
So how do these filtration-only cells stop that stuff from getting into the ground?
The absolute key feature is an impervious liner.
A liner, like plastic.
Yeah, often a really heavy-duty plastic geomembrane or sometimes a special geotextile. It completely seals the bottom and sides of the cell. It basically creates a contained bathtub,
Okay.
so it acts as a total barrier. Any pollutants that get filtered out of the water are trapped within the cell materials. They can't leach down into the soil or the groundwater below. Then the filtered water is collected by an underdrain system and piped away safely, keeping the contaminants contained. This type was actually super important, for example, in cleaning up old industrial sites around the Great Lakes. Preventing any more ground contamination was absolutely critical for bringing those areas back to life.
That's a really crucial difference then, almost like surgical environmental protection for sensitive spots.
Yeah.
So, okay, we've got these 4 types, but beyond picking the right type, it's also about where you put it and how big it needs to be, right? What goes into designing these effectively?
Well, one of the really great things about bioretention cells is just how versatile they are when it comes to placement.
Yeah.
They're incredibly flexible. You can basically slot them in anywhere between hard surfaces, roads, sidewalks, parking lots, even right up against buildings, anywhere you can direct water flow into them. This adaptability means you can often retrofit them into existing urban areas quite well.
That flexibility is a huge plus. Now, what about sizing them? Do they have standard runoff coefficients, like some other green infrastructure tools?
That's an interesting point. No, not really, not in the same direct way. Unlike, say, a green roof or permeable pavement, which might have a more defined runoff coefficient.
Which is basically how much rain turns into runoff for listeners.
Right, exactly. Bioretention cells are just too varied in their specific design and where they're put to have one single coefficient number. But there are some really useful rules of thumb that engineers use to figure out roughly how big the cell needs to be based on the area draining into it.
Okay, rules of thumb. Let's hear them. Can you walk us through an example, maybe show the difference?
Sure, so if the bioretention cell design includes a sand bed layer, which helps with drainage and filtration, then the rule of thumb is that the cell's area should be about 5% of the drainage area multiplied by that drainage area's runoff coefficient.
Okay, 5%.
So let's imagine you have a 100 square foot piece of parking lot, asphalt maybe, so it has a high runoff coefficient, let's say it's 0.95.
Pretty standard for pavement.
Right, so you'd calculate 0.05 times 100 square feet times 0.95, and that works out to be 4.75 square feet for the bioretention cell. Oh, wait. My apologies. I think the source calculation was different. Let me recheck. Yes, the example calculation was 0.05, 100, 0.95 equals 47.5 square feet. Let's stick with that number from the source. So 47.5 square feet.
47.5 square feet. Okay, that's a decent chunk, but definitely manageable in many urban spots.
Yeah.
What if you don't use a sand bed? Does that change the size needed much?
It makes a noticeable difference, yeah. Without that sand bed, the cell needs to be larger to handle the same amount of water effectively. The rule of thumb then is about 7% of the drainage area multiplied by its runoff coefficient.
Okay, 7% now.
So using our same 100 square foot parking lot, same 0.95 runoff coefficient, you'd calculate 0.07 times 100 times 0.95, and that comes out to 66.5 square feet.
Wow, okay, so that's nearly 20 square feet bigger for the exact same patch of pavement. So that sand bed really does make the system more compact, more efficient.
Exactly right. Adding a sand bed can significantly reduce the footprint needed for the bioretention cell. That makes it a much more space-efficient option, which is often really important in crowded cities where land is expensive and scarce. These rules of thumb are super helpful for that initial design phase.
Okay, so when we sort of zoom out now, look at the bigger picture. What's the real impact here? Why should you, listening right now, actually care about these, sometimes quite small green patches you might see in a parking lot or along the street?
Well, the benefits are genuinely profound on both the environmental and the economic sides. Environmentally, as we've said, they slash runoff volume and pollution by treating water right where it falls.
That 90% figure for solids is still sticking with me.
It's impressive, isn't it? Plus significant removal of heavy metals, oils, even those microplastics we talked about. And maybe most critically, they actively boost groundwater recharge. Some systems can send thousands of gallons back into the aquifer after a single storm. That directly helps local water table levels, supports streams and wetlands.
And on the money side, because that's often the deciding factor in city planning, right? What kind of savings are we talking about?
It can be really substantial. By using bioretention, you can often reduce the need for huge, expensive, traditional stormwater infrastructure. Fewer miles of giant underground pipes, smaller or fewer big detention ponds. That stuff costs millions to build and maintain.
Right.
So bioretention cuts down on those long-term maintenance bills for the old engineered systems. Plus, by reducing runoff and localized flooding, it can even lower flood damage costs, which is another massive economic drain on communities. It really is an investment in a nature-based solution that can save cities serious money down the line.
So it seems really clear. Bioretention cells aren't just a sort of nice extra. They genuinely offer a more sustainable and often more cost-effective way to handle runoff in our towns and cities. It really feels like what low-impact development is all about, turning a problem into something useful.
It really does. They take what used to be a liability, stormwater causing pollution and flooding, and they transform it into an asset. Clean water going back into the ground, supporting local ecology, making our communities greener, more resilient.
Yeah.
I actually saw one once, a bioretention cell in this really harsh paved urban area. And somehow a little flock of birds had kind of made a home around it. Native plants were thriving. It was just a small thing, but it really struck me how these systems can help reconnect us to nature, even in really built up places.
And that feels like a perfect place to wrap up our deep dive into bioretention cells. We've journeyed through their, They're really elegant design, haven't we?
Hmm.
How they capture rainwater, filter out the bad stuff, nourish the ground underneath us, and remarkably, make good economic sense too. It's a simple concept, really, but such a powerful LID tool. Just
Mm.
harnessing nature's own ways of doing things for a healthier planet.
So now, maybe as you go about your day, we want to challenge you to start seeing these systems. Really look around. Check out your local parking lots, those green spaces in the city, even the strips between the road and the sidewalk. How many of those little green patches that you might have just walked past before? Could they actually be hardworking bioretention cells? Quietly doing a massive job for your community's water cycle,
Mm.
maybe even helping out those local birds you saw.
And think about what more could be done. Just knowing about them, being able to spot them, kind of changes how you see your whole town or city, doesn't it? It stops being just concrete and becomes this network of potential living systems. It gives you a new lens for looking at how we manage water. What small step could your community take?
Indeed. It really is a call to look a little deeper, appreciate that hidden living infrastructure that's working for us.
And that is it for this deep dive. For our next environmental application topic, we're going to explore another really fascinating nature-based solution: coastal resilience and the amazing concept of living shorelines.
Ooh, that's a great one.
So please join us then for another deep dive into how we can work better with nature.